All right, so today we're going to cover static text. So we're just we've got our font. We applied some colors. We started with a 1-bit font, 1 bit per pixel, so literally black or white, if it's easier to think of that way, 0 or 1. And so far we took that font and we expanded it up to a 16 bits per pixel font. And we did that with these lines here. This basically says what location in memory we're going to store that. And then this uses some color definitions to make it a little easier to see what we're trying to do. So we have two different fonts that we've created, but we can use a BAS feature here that's really easy, and it's the same as what we see in some of the other include files, and that is to create a constant. So really simple syntax, keyword constant, the name of the variable, or the name of the value, and then the value itself within parens. So constant, and we're going to call this yellow blue, and we'll take this value here and then we'll replace it with this value, and we will do the same thing here, and we will this one is a red silver. Of course, you can be as specific as you like, but odds are I'll change those colors in the future. So we're going to stick with these, but in the future we'll probably go with a white text, black background, and then here we might do a red text, black background, or similar. But for now we're going to stick with this. We've got some names, make this a little bit easier to use. And the other one that we're going to do, in many games and other programs, you'll use multiple frame buffers. So we're going to go ahead and do the same. We're just going to call this FB1. Take this value here, put it to there. We're not going to get into the double buffering quite yet, but this will make our font easier to use when we get there, and we'll see that in just a moment here. Okay, so all this does is take our actual font, expand it to 16 bits per pixel in memory, but it doesn't do anything with the text or the letters or those kinds of things. For that, we will need to create a new function, and I really like to write what I want the code to look like first, and then fill out the function from there. And I do have some example code that I'm working from, just to make sure I don't forget things. But I'm really am writing this from scratch. And you'll see by the mistakes that I make. So this is going to be pixel 8, and we're going to call this static 16. And so what that is this is an 8x8 pixel font, 16 bits per pixel. And the variables that we need in order to be able to draw our text to the screen is we need to know our font name, we need to know our frame buffer, then we need the top position, which I'm just let's see, we'll stick with multiples of 8 for now. So I'm going to say top left 16 pixels from, or 16 lines from the top, 16 pixels from the left. And then we need to, our text address, and we'll see what this is in just a moment. And then the length, or the number of characters in our text. So we're going to come back to those. So first we're going to take this extra align. Just anytime you're changing the types of data or those kinds of things in your program, it's nice to just make sure that everything's in alignment, if you will. So we're going to use, this is a BAS keyword of DB, which stands for data bytes. And we're going to write hello world. Really simple. So this will create our string, and it'll be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 characters long. So we're going to come up here and we're going to say 12 is our length. So we know that. And then here we are going to give it our name. And I'm going to actually use hello world text. Go with that. And we'll put that up there. And I'm going to take this same line because I really want to use both of our colors. I don't want to complicate it too much, but this will actually be good. And again, the first position is the rows from the top. And we'll go 32. So that'll leave a blank line and then draw our text. And it can start at the same position from the left, and that's fine. So that's the code that we need to make it work. Now we put the work in. All right, just double checking chat. We seem to be no questions yet. All right. So here, this creates the macro, and the macro is the assembly language instructions that are inserted in line in the code where we are. So here, coming back to our main code, the assembly instructions that will replace this line. Now, what we'll do is very similar to this one where we did this jump and link. We're going to call out to some other code that is actually going to be down here in the util.s file, and that will be our code in here. So we'll go through this here. So I'm actually going to copy this line here and just paste it there. So So here we are going to say font name, frame buffer, top left string. I'm going to call this label, and length. And as mentioned previously, the curly brace has to be on the same line as the macro definition, and then our close curly brace there. So here we're just going to load up our parameters, really similar to what we did previously. So we will say lia0 font name. Actually, these are addresses, so I'm going to use the LA. Again, there's actually no difference in the code that's generated, but it just kind of helps you think it through that it's an address. So then we'll put the frame buffer there, and then we're going to say A2 top LA A3 left. Now, for those that are paying attention, we're actually going to run out of our argument registers. There are only 4 defined by the standard. So I'm going to come back to this, but I'm going to start and I'm going to finish out what we're doing here. And then as though they existed, and then we'll fix that. And then here we're going to do a jump and link, and very similar to this, how they're identical, we're going to take this and put that there, and our NOP instruction, and right below here we'll put that in, and JR RA, and we're going to NOP. So technically our code will do nothing, but it will return and go about its merry way. So we're going to come back here. Now again, we've only got these registers to play with, that are intended for this function of passing arguments. So we have a couple of options, and I'm gonna use 2 of the different options here. So let's see, which ones do I want to use here? Okay. So the first thing, it's not a big deal for this length to be less than 64,000. In fact, don't think our screen will even support 64,000 characters. I think it'll support like less than 2,000. So I am going to change this instruction to ORI, which allows for a 16-bit value there. And I'm going to put it there, but I'm going to use the 0 register, so it'll clear any value that's existing in the register, the result register, A5, which we're going to fix. We're going to clear it, and then we're going to basically just take this value. Actually, you know what? Add I think, does the same thing, and I think it's a little more clear instruction. But add I supports negative values, so I'm just going to note here 32k by max length, because the add I will actually do positive and negative. No. We're going to end up with better quality data, better quality parameters being passed if we use a 16-bit value, because it's greater than 0 or up to 64 KB. But we've got this A5. So this is where we're going to do a little bit of a cheat. And we are going to make this V1. If you recall, the V0 and V1 registers are the return value for your function call. So, if your function returns a negative number for an error message and a positive number for success, that's passed back in the V0 register. And that's the convention used in C programs and such, how it translates into assembly. The V1 is kind of a free register in this respect. It's available if you wanted to pass back 2 values. from a function, which is incredibly rarely done in most C languages and such. So we kind of get to just use this one for free. We can still use the v0 to return a value if we wanted to. We won't be in this case, but because we're kind of abusing the v registers, I'd rather use the v1. The other thing is, because this is a single instruction versus a pseudo instruction, which we know that LA is going to expand to 2 instructions, we can take this and replace that NOP, put that in the delay slot, and so it saves us an instruction. Okay, so the other thing that we're going to do, now again, our top and our left values they're never going to be that big. 640 by 480 is our absolute maximum resolution on the N64. So both of those values, of course, can be represented in just a little bit more than 1 byte, but it does require 2 bytes. So what I'm going to do is I'm going to change this to be LUI, the load immediate, load upper immediate. We're going to put the top value, and this, we'll just note it's a 16-bit value. And then this one, we will use the ORI, and that is also limited to a 16-bit value. And that goes into the 2, which means this can go into the 3. And now we have passed 1, 2, 3, 4, 5, 6 parameters. Oops, I'm going to go ahead and comment out that line. I'm going to take out that. That's dead code. That's not clear anymore. So we passed 6 parameters using 5 registers when we only had 4 official registers to use. So a couple of nice little tidbits in there. Now I'm going to take this and very similar to what you see up here where I had the variables. I'm going to do the same thing here and just kind of move these things all around so that we know where things are. And again, that's kind of a merged field, so we'll add those little notes. And then just comment those out so that we don't have to worry about them. And this is done. We can leave this in. It's kind of a comment that shows an example of how it could be used. We'll just leave it. Okay. So real quick, let's do a little make in here, run our script, and it failed. So let's just kind of get this compiling here. Error, close curly without a matching open curly. Pixel 8 util include on line 17. So it can't find a match for that curly brace. It should be that one. There's a typo here somewhere. Oh. Okay, silly typo. Forgot the keyword. So we will try that again. And it compiles. All right. So all right. I'll go ahead and close that. And that is the font itself. Okay. Now, all right, so let's go back and think about what do we need to get, what do we need to know, so on and so forth. Let's see. So I'm going to grab this, and I'm going to do an underscore exit. That's just a little label, so that I can exit this this method quickly, because the first thing that I'm going to do is say BLTZL V1 and so basically if V1, if the length is less than 0, that's the LTZ, less than equal to 0, then exit out. There's nothing to do. And we are pretty sure that we're not going to make that mistake, but there's no point in wasting any effort if that is true. And it might cause some real problems in our code later on if we don't handle that error. So technically we should probably do this with most of our other parameters. Here, let's kind of keep them in the right order as we do this. So we know that our font name is actually, it's more of a pointer to the location where our font is. So if that is equal to less than or equal to 0, actually, if it is equal to 0, once again, the less than 0 really just means that that upper bit, the very top bit, is set. Yeah, it should still be good. No, the 8000 range, the upper bit is set. Here, let me just pull up a calculator. So if we set that, that's the 8000 range, which is our normal operating range for N64 programs. So that could technically show up as a negative, like that. And so all of those bits would be set, and it would be a negative value. So when we're comparing against memory addresses, we only want to exit if it is actually equal to 0. That means it's uninitialized. Now our upper and lower values, they may very well be zeros. That's just the top left corner, so that's just fine. A3, our string label, that is another value that we should be checking. It's another memory address, so that is fine. There's our A3. All right, so we've checked our input parameters there. I'm not going to go too far down the rabbit hole. We could definitely check the A2 registers, but we have to take it apart first into both of its components. And so I'd like to get a little further in how we're going to actually use that code to find out if we take it apart now or later, or however we choose to. So at this point, we're going to assume our parameters are valid. And I think the first thing that we should do is load a byte. We're going to use the T0 registers. Again, temporary registers should always be safe. Let's see, if we come back here, we're not actually using any specific registers. Everything should be fine. All registers should be fair game at this point, and it's tough to think about and tough to explain, so just kind of trust me. So we're going to load the byte from 0x0 A3. So we're going to load our first character into the T0 register. And one of the things that I said much earlier about our font, and here, is that the space character, which is our very first character, is actually the 32nd ASCII character. So what that means is here, after we load it into T0, we're actually going to use the add I because it supports negative numbers. So we're just going to say T0 minus 32. And so now it is the same 0 base as our font. Here, might help to be able to see the ASCII table, so I'll open that up as we go along as well. All right. So, as we're thinking about this code, right now we know that we're looking at the uppercase H. We have loaded that. We have set up the offset for our font. Well, actually, we set the index, the ASCII index. Our font actually has okay. So here, let's kind of talk this out a little bit. 1 pixel equals 2 bytes. 1 character equals 64 pixels. So 64 times 2 equals 128 bytes per character. But here's the other thing that we want to think about. And it's trying to think of the best way to explain this. The way our font is, our font has one character that is literally 128 bytes long in memory. If you think of it as just one straight string of bytes in a line, it's 128 bytes, but it needs to be stacked. So you take the first 8 byte, or the first 16 bytes. This is the number that I was trying to get to here, but it's an 8 by 8 font. 8 by 8. And so one row is 8 pixels, or 16 bytes. One row equals 8 pixels, aka 16 bytes. Okay, so the reason that we want to think about it like this is in order to take our font memory and apply it to the frame buffer, we're going to take our character, we're going to take 16 bytes at a time, and we're going to write that into the frame buffer. There's 16 bytes, that's one row of our character. But then in the frame buffer, we actually have to jump down one full row and back to the front of that line so that it lines up on the left side, and then take another 16 bytes, and then come down one more row, and do another 16 bytes. Each row is actually 320 pixels, because we're doing a 320 by 240 screen. And so 320 becomes 640 bytes per line on the screen. Once again, we're going to work through this, but I'm just kind of talking out the math for myself, and hopefully it helps everybody else's understanding at the same time. Okay. So the so this is our Ascii index, which we then actually have to multiply by 128. So even if our Ascii index is 0, which is a space, multiplied by 128, it still ends up being no difference. So this is tough. So here, we are going to add T1. We're going to take that 0 register, and we're going to add 128. So again, just really putting the value of 128 into the T1 register. And then we are going to say T0 times T1. All right, so here we're talking about the multiply instruction. The multiply instruction has a few little has some differences from the other instructions. Almost all of the other instructions, besides the multiply and divide sequence, are completed in a single clock cycle. I don't recall how many clock cycles it takes for the multiply and divide instructions. It's in the data sheet. I think it's about 10 for this case, between 8 and 10 instruction cycles. So while it's doing that, we can actually go on and do some other work. In fact, yeah. All right, so that will then give us our index into the font. And so while we're waiting for that to complete, because it does kind of work in the background here, it'll be blocking up to a certain extent, and we'll see how to get the value out once we've calculated it. But it will kind of do this in the. I think that there's like it takes one instruction one cycle to cause an interlock, and then you can do other things, and then yeah, it's I don't know it exactly, but it should be just fine if we as long as we give it a little chance before we try and pull the value out. So what can we do? Let's go ahead and find out where to start in our frame buffer. So let's see. So let's get our top row, the number of lines from the top, and so that is in A2. So I'm going to use and I. We're going to put this in T2. We'll take the A2 register, and we're going to... Oh, that's not going to work. We'll use the and I for the lower. To get the upper, we can use shift right logical and 16. So this will take the value in A2 and shift it to the right 16 positions. So T2 equals A2 16. That would be the C kind of a syntax for that function. And then we're going to go ahead and continue to use the A2 register to hold the lower value, but we will do the and I A2 with 2, 3, 4 Fs, and so that will remove the upper 16 bits of that register. And all right, so that is good. At this point, let's see. I'm going to take this label here. I'm going to insert it there, but it's not the exit. It is, I'm going to call it next car. Okay. So with T2, because that's our rows, we do have to multiply by 320 in order to know what position or what row we're going to start on. Actually, it's 640 bytes, 320 pixels wide. So I don't think we can do this, but where is that? Well, actually, here we go back to programmer. We go to decimal, we say 640. It is not a direct power of 2, so we can't multiply that quite like I want. All right, once again, I'm talking this through and writing this live. So at this point, we should have our interlock on the multiply, and so it will actually block until it is complete. And then we're going to use this instruction mf low, which means to move from the low register. And so if you look at the multiply instruction up here, you can see that we pass in the two operands, the two values that we want to multiply, but we don't specify the result. And that's because in the MIPS processor, the result is always placed in the MF high, or I'm sorry, the high register and the low register, which are separate from our standard 32. And so we actually need, there's an MF high, MF low, MT high, MT low, in order to move a value into those registers. So we have those extra instructions to manage those extra registers that we have. So we have, and so this is going to automatically take it from the MF low register and put it into whatever register I specify. And the T0 is still our character index. How about we put it into T1? T1 was kind of a scratch register on this add. And so that is all we need. So the result will now be in T1. So okay. I forget. Once again, the rules around the multiply are a little more involved than I might have liked. But here we're going to take the T2 register and multiply it by T3. But I need to put my value into T3. And so I'm going to use and I T3, the 0 register, and 640. That is the number of bytes in a line once again. And so we'll now take T2, which is our top row location, multiply it by 640, and then once again we need to do something else for just a moment until we can pull that value back out. I'm going to go ahead and write that there. Okay. And and while that's happening, we can take our left position, which is still in A2. Here we masked it off, but here we can shift left logical on A2. A2 is the destination register and the source register, and we're going to shift it to the left 1, which is the equivalent to multiplying it by 2, which is 2 bytes per pixel. So again, in our example call here, we said that we're going to do 16 pixels from the left, which is actually 32 bytes from the left. And so we took 16 and made it 32 by doing a shift left logical 1. And now and then we have our T3, so all right, so we still need to remember our original frame buffer value. So we don't want to lose that in our other calculations. We don't want to reuse that register for anything. And the same goes with our font name. We're not going to write to those registers in this code. Even the string label, we probably won't. Okay. So what we need here is we're going to start adding. We're going to use T4 as the destination register. And we're going to start with A1, which is our frame buffer, A1. And then we are going to add our A2. And that is good. I'm going to go ahead and move this instruction down one more. And then here we're going to add one more. And again, our destination register is T4, but our source register is T4 plus T3. And so this should give us our first location in the frame buffer to write our first 16 pixels of our character. Okay, so first we have to get our pixels, and we're gonna, since we need 16 bytes, I'm gonna use the load double, and I'm just gonna put this into T5, and I'm gonna say 0x0, and here T1 is our font position. So we're going to read from 8 bytes from T1 and put it into T5. We're going to copy that line because, again, that was only 8 bytes. We're going to do into T6. Since we know what we're doing, we started with offset 0. Then we're going to start with offset 8. And we're going to load the next 8 bytes. And then we need to store double. And again, we're going to use our T5, 0x0, but this needs to go to T4 and store double T6, 0x8 into T4. And that is our first line of our character, written, taken from the font and written into the frame buffer. One line, 8 more lines to go. So now we need to go back and figure out, kind of rearrange and insert a label here somewhere, so that we can do our second line. So T3, yeah, I kind of lost track what all these registers are doing now, because register names are not nearly as intuitive as they could be. So let's go ahead and take just a moment to kind of label things out here. So, well, we know our A0, our A1, A2 is just the lower, it's the T registers here. All right, so T0 equals Ascii Index of current character. Actually, it is the pixel 8 minus 32, or actually ASCII minus 32 pixel 8 index of current character. Something like that. It's a little long, but we'll get there. T1 is the font index. And again, this is at this point. It was kind of a scratch character just above this, but T1 equals index character index in font memory. Okay, and T3 is, and again, we kind of use T3 as a scratch register for just a moment there. Up here, we used it for just the 640 value, but then we got our working value here. And so here, our T3 is equal to our frame buffer index right location index in frame buffer. Yes. And in between we used T2, which was A2, and so here I'll just go ahead and note that T2 equals the top value, or row screen row. And oh, no. T4 is the right location in the frame buffer at this point. And T3 is the row location in index in frame buffer. Something like that. Again, we need to kind of figure out how we're going to get to our next rows. So here we know that add I T1 equals T1 plus 16. So that's just going to move us to the next 16 bytes, the next row in the font. And then we need to add T4 640. And that will take us to the next row. And And so we need to loop through here 8 times. So I'm going to say b equals 0. T7, 0. And here I'm going to do add I, T7, T7 minus 1, which means up here I need to say add I, T7, 0, and 8. And I'm ready to test. And it's about time. So if my testing goes well, the goal is that I can write a single character on the screen. It will be, ideally, of course, the uppercase H in Hello World. So we're going to have to come back and we're going to have to figure out how to move it along to the next character and so on and so forth. But I would really love to see one character on the screen at this point. And all right, so we have an error here. Assembly failed. Okay, so malformed expression, b equals to 0, go to exit, line 37. So the extra L at the end stands for the likely, and I'm not using the delay slot here. I'm just putting a NOP in, so the likely doesn't actually provide any benefit here. So that was kind of a something I didn't have to do. Malformed expression, it still doesn't like BEZ. We can change that to B equals 0. Let's test that line. Yeah, we're on to line 39. So we'll just do the same technique. We're just testing if it is actually equal to 0. Oh, forgot the comma here. Line 78. Okay. Sure enough, I did. All right. We are compiled. So we're going to debug video. Hold on. Way up here, I forgot to change it to number 9. So we've been generating that one. I'm going to go ahead and delete that and make again and debug video 9. All right, we're really hoping to see something that looks like an uppercase H. Once again, our default breakpoints are already set up. We're just going to go ahead and say F5 to continue. We've got all of our initialization code, but if you look back here, you can see that we inserted some NOPs, and those are they're really great for helping us find the code we're looking for. So we've got 3 NOPs, 2 function calls, 3 more NOPs, and these are the function calls we really want to look at. So if we look in here, we've got a JAL and a JAL. Those are our 2 function calls. Those are our 3 extra knops, and here is our new code. So I'm going to do F9, which sets a new breakpoint, and F5. Oh, okay. So I'm just going to point out, we do have kind of a goof here. We're going to go a little bit further, but I'm just going to point out this goof. The memory locations here, where the 2 fonts are placed, actually exist inside of frame buffer 1 here. So we are technically going to overwrite some of this memory, but I don't know that we'll get that far. We're going to watch our code execute and see what we get. So I'm just using F10 to step. I'm coming up on this JAL instruction, and I'm going to do an F11, which is a step into, because I want to see what happens in there. And here we can see our 0 checks, and we were good and passed good values, so the 0 checks do not error out. First, here we're loading our first character, LB, load byte into T0. So T0 is now equal to 48. So I'm just going to close that because I just want to get to ASCII table. And we're looking for 48, and we're looking for hex 48. So we are hoping, yes. So here is the uppercase H, the decimal value of 72, but the hex value is 48. So that is a very good sign. And so that is what is in our T0 register over here. Then you can see that our add instruction was actually converted to a hex value, subtracting hex 20, which is 32. And so now it is 28. So that is good. We went from 48 to 28. And all right, so if we go back and look at our code, here, this is what we're doing. So 128 pixels, bytes per character. That's what we're moving. And here is our multiply, T0 to T1. As I mentioned, we have the high and the low register that are down here. They're just beyond RA, which is register 31. So these are just extra registers. And so when we execute that instruction, we can see that the low register is the one that has a value, T0, T1. So 28 times 80, and again, that is in hex. We'll come over here, 28 times 80 is 1400. And so that is correct. Then we have shift right. So this is how we're getting our top, our rows value for positioning our font. We're taking the value A2, which is quite, oh yes, so it's 16 in hex. I'm sorry, 10 in hex is equal to 16. And so that ties back to the 16s here. And so that's what we're seeing in the A2 register. Kind of have to squint a little maybe, but it's 0010. That is the value of 16, and and it's doubled up here. So after this instruction, T2 should be equal to 16. F10 to step, and there that is, so that's good. And then here we're going to fix up A2 to also be equal to that 16 or 10 hex, and that is now correct. And then we take our value from T1, which we took it from the low register and put it into T1, and now we're dealing with that 280 value, which is the 640. And again, we had that other multiply. So now all of our things should be correct, and we're going to start copying some pixels to the screen. So let's kind of see what happens here. Oh, that was not good. All right, so what happened is I accessed some bad memory. I'm betting that the T1 register wasn't set up like I wanted it to be, or something along those lines. In the N64, the exception handler for a bad memory access jumps to this 8,000 register, or the 8,000 memory range, and executes the instructions that are located there. In this case, we didn't put any specific code there, so it's really still like the original PIF code, the BIOS code, and that's not going to end well. But there's still some good information that we can get, and the trick is to look down here. So down here we have the exception PC. The PC, if we look here, is wow, I'm sorry, I'm forgetting the name of this, but this is basically the instruction that is currently executing. And so if we look down here, we see that it's the 801204. So we can go to a new disassembly window, and we can type 812301204, and we can see that it is the LD instruction as we kind of thought, and so odds are the issue was with the T1 register, and the T1 register has a value of 1400, which is completely invalid. Yes, it is. So here we did the multiply into the font memory, but we did not add the font base, the font name A0, to the T1 register. So that is what went wrong. And to do that, we probably want to come after T1 is there. We will do an add T1 equals T1 plus A0. All right, so because I know this is just going to go sideways, I'm just going to end that. Wait for that to finish, and okay. So again, we're going to do our F5, get up to where our code is, just scrolling down, looking for our NOP ranges, and this is where we want to be. Set F9, set our breakpoint, F5 we run again, F11 to step in. Oh, and there we see our first 2 pixels are at the very top there. That's not where we wanted them. We wanted them 16 rows down. So we'll get there, but let's kind of see what we end up with. Okay, so T7 is equal to 7. So I said if it's equal to 0, jump back. What I wanted to say was not equal to 0. So I'm going to come in here, change this to BNE, and we will try again. But we did get 4 pixels, and they do look different, and they could technically be the start of an H. So pretty exciting. So we'll go ahead and close that down. I'm going to go ahead and clean up this frame buffer thing between our font and our frame buffer memory being shared. And real simple, I'm just going to change those up to, those are now going to be in megabyte 2 of RAM, and this will still be in megabyte, oh, I'm sorry, this is right at the, so all of our code is copied into megabyte 0. The frame buffer is in megabyte 1, and our fonts will now be in megabyte 2. So that's, it will keep those separate. And so here we go. Alright, I'm really just waiting for MAME to do its thing here. I seem to have some slowdown here in my virtual machine. MAME is a pretty intensive application, and it's virtualized and everything else going on, but it usually performs better. So at my next opportunity, I'll probably take a little break and see if there's some improvements I can do. Alright, so we've already got our default breakpoints. Just really going through the exact same steps as before. F9, run to there, F11 to step in, and oh, okay. Ah. Okay, well, that is not what I was expecting to draw there. So, all right. I've been trying to keep these streams a little bit shorter. We're pushing an hour 15. I'm going to go ahead and call it, even though we're incomplete. And I feel bad about that, but I'm not sure what's wrong, and this could go a whole lot longer because of that. So I'm just going to take a little break, figure out my CPU usage, and take another stab at this. Might be tonight. No, won't be tonight. All right. Thank you so much for watching.